Good morning, Tensor friends. In one of my videos, I created some confusion because I didn't explain it well over a covariant inner product, two covariant basis vector inner the products, and a covariant and contravariant inner the product. And I'm pretty sure the reason we keep getting confused over these things is because we're also used to working in Cartesian, the systems, where all of these are true because the system is orthonormal and the basis vectors are the same everywhere. They don't change anywhere in the space. So this inner product is the identity matrix, and this one is, and they're all the identity, the matrix. Well, I thought, hey, let's just go do something completely different. Let's look at a coordinate system that is not orthogonal. It's called an affine, the system. Okay, so this is still in Euclidean space, which means all of these coordinate lines are all parallel, but you can look at them and see that they're not orthogonal, that none of them are orthogonal. Okay, so what I did here is I popped in a Cartesian, the system, and I picked a point. So I just said that's the origin. And I went out here and I found this point here. And I went out here and I found this point here. Okay. And here's my best attempt at finding those points. Now I added this little unit vectors here because I need some way to count in directions, right? That's why I added these. So the covariant, the basis vector E1 had these components and E2 had these components. And they look like this. Okay, so I had the E1 and E2 just follow the coordinate lines, and I made them the length of one side of this. What are these things called? Trapezoids. And E2 like this. Now you can see these are definitely not orthogonal. Okay. So what we're going to do now is use these two that we found to find the contravariant basis vectors. Okay, and the first step in doing that is to find our metric, the tensor, right? So we take the dot product of E1 and E1, right? So this that squared plus that squared is this. And then E1, 2 is the dot product of E1 and E2. So that times this plus this times this equals that. And then 2, 1 is the same. And 2, 2 is this squared plus that squared. All right, so now we've got our components of the metric tensor. And you notice that none of these are 1 and none of them are 0. They're all different. But once again, the tensor is symmetric across the diagonal. Okay? Now, we need to find this is the covariant metric tensor. Now we need to find the contravariant metric, the tensor, which is the inverse metric tensor. So what I did was went to a matrix calculator online and plugged these numbers in, and here's the inverse because it's a lot of work to do it by hand. Okay, so now we've got our covariant metric tensor and we got our contravariant metric tensor. Now we can use what we already understand, how to raise and lower indexes. So we want to raise this index to a contravariant position. So we multiply the covariant position times the metric tensor components that we need. All right, so let's get started. All right, so we want E1. So I is equal to 1. So we put that in. There's a 1 and there's a 1. And now look at this JJ. This is a summation index. So we've got to sum over all of the dimensions we have. We only have 2 dimensions. So in the first case, J is 1. In the second case, J is 2. So we go up above, we pick out all these numbers because we have all this stuff on this side of the equation, right? So we put all that in, looks like this. We multiply all that out, bada bing, and we get E1. So now we've got an expression for the contravariant, the basis vector. Now we got to do E2. So it's the exact same the procedure. In this case, I equal 2. So you put your I in, 2, 2. Then you do your summation. So in the first case, it's 1. The second case is 2. We go up above. We dig all that out. And now we got it. All right. So now we have both of them. So let's go look at them. Okay. So now that we found them, we can plot the first one. And I'm using prime here as the contravariant. So unprimed is a covariant, prime is a contravariant, because I don't know how to, I can't make this thing do indexes, ups and downs. All right. So here is E1. So this is the contravariant basis vector E1. And here is E2, the contravariant basis vector. All right. Now let's go back and look at what we can do with them. Okay, so now we can answer this question. What is the contravariant basis vector inner product with the covariant inner product with the contravariant inner product? Because we're in a non-orthogonal, the coordinate, the frame, right? All right, so the first thing we do is let I equal j. All right, so we got E1 dot E super 1. We calculate that out, and you can see it's 0.99999, because these numbers just go on forever. And if you did this in a spreadsheet, you'd probably actually come out with one. I just did it with a calculator. All right. So E1 dot E1 is equal to 1. Well, what is E1 dot E2? It's equal to 0. Well, what's that tell us? Well, what that tells us is what we expected to happen. If you tilt your head a little bit to the right, you'll see that this E1 contravariant basis vector is orthogonal to the covariant E2. Do you see that? And once again, with your head tilted, you can see the E1 covariant basis vector is orthogonal to the E2 contravariant basis vector. Okay, so that identity works. And it works in non-orthogonal reference frames as well as orthogonal reference frames. All right, I hope that helped, and I'll see you later.